Visible, sir.
Okay. So, good morning, everyone. Good evening, everyone. Myself, Chaitanya Kumar from Electrical Department, IIT Madras, and welcome to the tutorial 8 of Analog Electronic Circuits. And today we will be discussing problems based on differential amplifiers. So before I start the set of problems that I have, does anyone has any doubt in the present uh, assignment or present week's content?
I have doubt. I gone through the recording session, sir, last week. So,
Okay.
sir, I'm getting doubt in a small signal analysis. The if input is connected in a unity feedback configuration, how to approach the small signal analysis and all. I'm getting confused over there, sir.
Sorry, I couldn't really understand. What is the problem in that?
Sir, sir, if inverter is there, we'll mention it with a digital that symbol, right? Yeah. If it is connected like this, yeah, unity feedback configuration, yeah, whatever. Mm.
Okay, you are
Sir,
talking about this.
yes, sir. If there many inverters are connected now, sir. At the time, how should I approach, sir? Everything. I mean, to every inverter, I need to write small signal analysis. It will
Yeah, of
become a
course. You need to write small signal analysis for every inverter. One thing that you can see is that every inverter is basically what? Like instead of making that complicated, uh, just instead of making that complicated small signal model like this, that you have basically this model. So this model might be a little inconvenient to write and might be a little inconvenient to work with. So what you can use is, as we discussed last time, you can model this as a transconductor of value with a transconductance with a value. So it is a bubble transconductor. Why it is a bubble transconductor? Because it basically sinks current. Whatever voltage you give, it sinks current that is proportional to the input voltage. So you can model it with this. Its transconductance value will be GMN plus GMP, and it will have an output resistance of RON parallel ROP. So this is a much more convenient representation. You can use this to do the small signal analysis instead of using this representation. This is, I agree, this is a little confusing when you have multiple of this thing in a circuit. You can try using this and then carry on.
Yes, sir. Sir, sir, could you, sir, I'm in week five. I'm getting confused over an sign, sir. Negative feedback. Could you recommend any lecture series or any specific book, sir? I tried, but I'm not getting familiarized with the topic.
Uh, no, so negative feedback as in like what exactly? Uh,
We need to determine the signs, right? Which one is inverting, which one is non-inverting.
Okay, so you can use any circuit that you have. For example, in any book, wherever you find circuits with negative feedback, you can look at it. If it has the sign of the op amp, you can try to reason why the signs of the op amp make sense. For example, a very simple case, you can say, let's say, you have learned about active RC filters in some of your
Hmm.
other courses. I hope. I
Yes,
hope.
sir.
Okay, so like active RC filter basically looks something like this. So you have an input resistance, uh, you have a capacitance like this, you have a resistance with value QR that basically sets its quality factor, and then you have uh, inverting amplifier. Then basically you have an undamped integrator, and then you have this thing.
Resistor.
-1, or -1 is not needed over here as you have already inverted it once.
Sir, we can write resistor right here for a for current, right?
Sorry?
We put a resistor right
Sorry,
here.
sorry. Yeah, a resistance over here. So basically, if you want to see the op amps signs, what this is a fairly I think this will be a fairly a comprehensive example to implement to see the negative feedback, to understand how the signs of the op amp work. So one thing that you should make sure is, so you can see here that there is a big loop over here that basically encompasses the complete complete filters, this thing. And there are three small local loops in this. And in order for your circuit to be actually stable, you should make sure that each of the small loops and the overall big loop, all of them are having negative feedback in place. Okay. So we will first of all look at these three small loops. So in these three small loops, can you quickly tell me what will be the sign? So let's say I consider this loop first.
Mm.
Okay. So here what we will do is, in order to check the sign, let's say I break my op amp's path over here. So what I will say is, so let's say I give some Vi signal over here. Here, depending on the sign of it, here it will be again, if you just go about, let's assume this is negative and this is positive. Okay.
Mm.
Let's assume, so here it will be some minus alpha Vi, where alpha will be some positive quantity, positive frequency dependent quantity. It can be anything. So minus alpha Vi you will have here. And since this is just a passive network over here, so this won't impact the sign of minus alpha Vi. So minus alpha Vi will remain like some minus alpha into some beta because of this another network. Minus alpha into beta Vi will come over here. So basically, you are seeing that if you put an inverting terminal at the at this node, that makes the whatever goes through the loop, whatever comes back is a negative of what you have given. So that means to say that your sign are correct, and this particular loop is stable and is in negative feedback. Similarly, for this loop, if we disconnect over here and apply some Vi over here, so and we have negative sign over here. So what happens is, uh, we get what we get is basically, again, we see that we have a negative. So we basically, if we have Vi over here, we will have some minus alpha Vi at this node, and the same thing will some minus some alpha beta times Vi will come at this. So this no, loop is also having negative feedback when you have signs in this way. You understand?
Yes, sir. Yes, sir. Sir,
Similarly, for this one, now for this one, can you tell me which will be negative, which will be positive?
sir, negative will be ground will be non-inverting terminal positive.
Positive, and this will be negative. Okay.
Mm.
Now let's see that whether this complete loop is having negative feedback or not.
Mm. Mm.
Okay. We will look at that. So uh, what you will do is, again, we will uh, basically, let's first of all remove this inverter. We will see why this inverter is required. Let's say, so that inverter basically just give a -1, right? It is not going to impact its frequency response. It's just an all pass -1 filter. Where should we disconnect to apply the test voltage to compute the signal? Generally, you should take a high impedance. In Cedar Smith, he has put some same resistance back, so that, see, like as far as like if you want to calculate the actual loop gain, In that case, you should make sure that your all those the transfer function, basically the structure of the circuit doesn't changes. So in that case, you should do all that. But let's say you are just doing for quick computation of signs. In that case, if you know that there is a passive element, it is not going to impact the sign of the signal. In that case, you can do it. But you can ignore for example, this resistance over here. For example, this resistance, whether it is there, it is not there, it doesn't matter. So it won't change the sign of the feedback. So that is the case. And generally, like while computing the loop gain and all, you should always cut your path at a high impedance node. So what is a high impedance node in this case? All the inputs of the op amp are high, considered as high impedance node. So you should always cut your path at high impedance node, so that there is no just a minute, so that there is no loading effect and all when you are actually computing your loop gain. So that you should keep in mind. Okay, so moving forward, so now we apply Vi over here. First of all, let's what we were considering is, let's say this inverting amplifier was not there. In that case, what will happen if you apply Vi over here? You will get minus alpha Vi at this node, and then this minus alpha Vi will get again inverted by this integrator, because it has a negative sign. It's a transfer
Sir, it
function
will
is by.
result as a positive feedback, right? In this case.
Correct. It will result as a positive feedback. I think now you are able to understand it. So you cut a node at a high impedance, cut the loop at a high impedance node. You give a Vi, just keep on checking the sign after every block, and whatever you get in return, if it is in the same, if it has the same sign, if it has a positive sign, then that means to say that you are in positive feedback. If it has a negative sign, that means to say you are in negative feedback. Okay, so basically you see that basically you have two inversion in this, then that means you have positive feedback, and that is the reason that you require an inverting amplifier with unity gain, my gain of -1. So you have R over here and an R over here. So basically it gives you a gain of -1 and it makes overall loop stable. So that is the function of this block. Okay. So I hope you understand this example.
Yes, sir.
Okay, one more example we will do. So now let's say we have this thing over here. So we have a resistance over here, and then we have,
Yes, sir. Non-inverting amp. Yeah. So both
we
of
say, we let's say we have something like this.
okay.
In this case, how will you say whether your circuit is in positive feedback or not?
Sir, based on the output voltage, output differential voltage.
Based on the, sorry,
So, for example, if both inputs are grounded, based on the offset voltage, we can say either it is.
whether no, but there is no input to it, and I'm saying that let's say the op amp is ideal, you don't have any offset voltage.
Okay.
So yeah, whichever FB is more, whichever beta or FB is more. For
Hmm.
example, so in this case, the difference was that I like one of the terminal of the op amp was grounded, so I applied signal at one particular terminal only. But when your both of your terminals are not grounded, then you have to apply a differential signal to the op amp.
Hmm.
So
Yes.
in that case, you will cut the op amp like this. So you will cut the op amp over here, and let's say you apply a Vi like this. Okay, you apply a Vi like this. That means the positive end of Vi is on this terminal, that is the negative terminal of the op amp, and the negative end of the Vi is in on the positive terminal of the op amp. So here you will get some, because this has an inverting effect, you will get some minus Vi at this node. Okay, let's assume this is a diff to single-ended, diff to differential to single-ended circuit. So you will have minus Vi over here, and then at this node, at node A, what will be your value? It will be minus Vi minus alpha Vi over here, and then it will be minus alpha Vi by 2. Why by 2? Because you have R and R, resistor divider between two equal resistances will result in the voltage getting half. And in this case, you will have basically zero point 0.5 by 1.5 times alpha Vi. So yeah, correct. Sorry, minus of alpha Vi by 3 at node B. Now, again, you see that in this case, node A has a stronger, node A has basically a stronger feedback factor. So in that case, basically the terminal which will basically have a stronger feedback factor, as one of you guys pointed out also, that will basically determine the sign of the feedback. In this case, it happens to be node A, and which is correctly connected to the negative terminal. So, my point is that you will keep on encountering these kind of circuits with op amp in negative feedback across your textbooks, and there you will I don't exactly remember or don't exactly know like if there is a systematic exercise where you have lots of circuits where you can practice that, but even if you don't have that, you will keep on encountering these kind of circuits across your the various books and all, and in all of them you can try to rationale that whatever sign of the op amp has been given, why have they have been given with these kind of logic. And let's say you come across a circuit where you cannot understand the reasoning to that, you can always come in the tute and discuss that particular problem. So
Sir, sir,
yeah.
with like these circuits, I'm comfortable, sir. If op amp and MOSFET is mixed now, at that time I am getting confused, sir.
Okay, so in that case, basically, you should understand that what is the sign of you should identify. So basically, the whatever circuits you encounter, you can always find whether it is the transistor is connected in a common source configuration or a common gate configuration or a common drain configuration. Okay, if let's say you encounter a common source, that means to say the sign of the from input to output will be inverted. If you have a common gate or a common drain, in those cases the signs of the input and output will remain the same. Okay, this much you can keep in mind and try to solve the questions. For example, let's say we have this question over here. Let's consider two examples. So one is this, another is this. Okay. In both the cases, you need to find out the which terminal has to be positive, which terminal has to be negative for these two, both of the circuits to be in active, be in negative feedback. So
Sir,
let's
first
start.
circuit, yes, sir.
Yeah, tell me.
So first circuit is common drain amplifier, right? If common drain amplifier, input and output should be in phase to each other.
In phase
So
to each other. Okay.
yes. Mm. Second circuit is a common source amplifier, current loaded.
Yeah.
So input and output are inverted. So
Correct.
based on that, means we need a loop. We need a input voltage to be in phase, right? Uh, upper terminal should be positive, lower terminal should be negative, sir.
In which one?
First case, first question number
Correct.
in common train.
Yeah.
In second one, it is a reverse.
It is reverse.
Mm.
So, yeah, so you understand how it is working, right? Like, irrespective of whether it has whether it has op amp, these macro model of the op amp, or it has transistors, or it has mix of it. In every case, like there are two principles. First, cut the loop at a high impedance node, and second, like give some voltage and just see as you traverse through the loop, what is the sign changes. For example, like if there was complete circuit instead of a macro model, let's say you had this thing over here. I am just trying to like make a circuit which can basically help you with this thing. So now let's say you have this. So this is connected to some bias voltage. So let's say we have this circuit. Now this looks like a fairly complicated circuit. Okay. Can you tell me whether this circuit is in negative feedback or positive feedback? So first of all, you should identify, like first thing what you should identify.
So we should break the loop, right?
Yeah,
We need to get the outputs of each stage. First one is common source, right?
this is a common source.
Mm. Then
Then
next one is common drain amplifier,
common drain.
a gate.
Then this is a common gate.
Again, it is a common drain, right?
This is common drain. So
Yeah,
where will you actually break the feedback, break the loop?
yeah. Before the common source.
You let's say break it before the common source. Okay.
Mm.
So if you give some vi over here, what will be the voltage at the output?
Yeah, it is inverted, sir. Inversion of GM into
Minus some alpha vi. Okay.
mm,
And
mm.
then what is over here?
Yeah, alpha VI.
Alpha vi or minus alpha vi?
Yeah, minus alpha VI, sir. Same.
Minus alpha vi, assuming it is common drain with a gain of 1. Okay. Now
Mm.
what happens now?
Yeah, here we current will get flown, sir. What and all current is
With
getting, sir.
where okay, so what will be the direction of the current from here? This will so it is red arrow or the green arrow?
Sir, it should be black carrier, sir.
There is no black arrow here.
Sir, not red arrow beside us. That one is
It should be
green arrow, sir.
green arrow, correct.
Mm.
So if it is green arrow and no current can flow in this direction, right?
Mm-hmm.
Because like no incremental current can flow in that direction, because that is basically a open circuit in incremental analysis. So the same current will flow like this. Okay. So if current is being pulled out, in this direction, what will be sign of voltage over here?
Hold on.
Incremental voltage.
Hmm.
It will be minus.
Yes, sir. Yes, sir. Because it is
Okay.
going this side, right? Means if
Yeah.
you take KCL, leaving should be negative.
Yeah. So
Hmm.
if this was minus alpha Vi, this will be something minus alpha beta times Vi. Okay. Now, if this is minus alpha beta times Vi, what will be the voltage at this this thing?
Yes, sir. Minus alpha times beta times VA into sum.
Minus alpha times beta times Vi. And
Hmm.
then what will be the voltage over here?
Yes, sir. Minus alpha times beta times VI minus.
Minus alpha times beta times, let's say some gamma times Vi. So
Hmm.
whatever voltage, input voltage you gave, you got a negative of that particular input. So
Hmm.
that means to say that your circuit is in
Negative
negative
feedback.
feedback. Okay. Now, one more thing. So I said that it is important to break the loop at a high impedance node. Now, this need not to be this high impedance node. You could have broken the loop over here also, over here also. Okay. So in both, like no matter where you would have broken the loop, you would have got same kind of response. However, let's say if you have broken the loop over here at this place, then what will happen is although the sign that you will get from this complete this thing will be correct, but if let's say this had some non-zero output resistance RO, in that case, the magnitude of the loop gain that you get will be incorrect. Why? Because in actual, let's say you broke the loop over here. Let's say you broke the loop over here. So what will happen? You will apply an input voltage over here. Then through the complete loop, you will get some output over here. And if you get the output over here, so like in actual practice, this particular resistor was loading this node. But now, since this particular resistor is not loading this node, here you will get a value that is higher than what actually would have been. So you should be careful. And to let's say you didn't want that, then you should while breaking the loop over here, you should have put a resistance of the same value at this node. So, like in order to avoid these complications, we generally say that you break the loop at any of the high impedance nodes. There, basically, the high impedance is not loading the previous stage. So, even if you break the loop, it basically has no impact in the actual gain, in the actual loop gain. Is this clear?
Yes, sir.
Okay. I hope you get the idea of how to approach these kind of problems.
Yes, sir.
Yeah. So, wherever you find these kind of circuits, you can try to apply this principle and get the signs of the op amp, signs of the circuit in negative feedback. Is it clear?
Yes, sir.
Okay. So, any other doubt?
Sir, you gave reference to the fixed the transconductance transconductance, sir,
Fixed
previous.
fixed trans GM, fixed transconductor.
Yes, sir. Yes, sir. Sir,
Yeah.
we can implement it. Means, sir, if I have access of 28 nanometer technology and all, to implement the same circuit in Cadence, what are the things we need to do, sir?
So to implement it in Cadence, see 28 nanometer technology is a very low technology node. So
Mm.
in that case, first thing is that your square law model won't work.
Mm.
So basically, you know about MOSFET characterization,
Yes, sir.
GM by ID method or I per W method.
Yes, sir. I know, sir. GM already
Okay,
method.
so you just use that to determine the width, length, and the current density of the transistors that you want, and
Mm.
implement that circuit.
I mean, will it be same, sir, or else we need to make any modifications, sir?
What do you mean by that? I didn't understand.
Sir, for in ideal case, you have been discussed, no, sir, for fixed transconductance. If it is a no, non-ideal case, then circuit become very complex, no, sir. You give
No,
before.
the non-ideal case was also discussed. No, uh, that was discussed in the paper, the reference paper that I have posted in the group, in the chat.
Yes, sir. Means it will give reference, sir. I mean, means if I want to proceed with, means what are the things I should do? That is the thing.
Um, that's what so whenever you are actually designing a circuit, you first of all you should keep in mind that this square law model doesn't work, and to in order to actually uh, set the current density and width and the length of the transistors, you have to use MOSFET characterization using GM by ID method. You do the first iteration, run the circuit, and if like yeah, you have to do two three iteration to get to the final product.
No, sir, if I want to know, I mean, so after designing a circuit, I would like to know either it is means it is invariant to the PVT invariant process voltage temperature.
Hmm.
How can I check, sir? Either it is a means
You can use the DC analysis, no? Like
this
you can in DC you can basically get the operating points of the transistors in question, and the transistors whose GM you have to fix. You can get the DC operating point of those things. In DC operating point, you will have the list of parameters. Let's say it will have GM, GDS, and VDS, VDSat, all these things. You can take GM and do a temperature sweep. First of all, do the temperature sweep. If you see that and like plot its GM with respect to temperature. If you see that it's constant, or let's say uh, I mean, basically, it won't be exactly constant. It will be constant with respect to what you would have got if you would have put a fixed current inside that GM. You can compare those two. So those things you can do. Basically, you should use a GM sweep.
okay, okay, yeah, sir, I get idea. That's yes, I will.
Okay.
Thank you, sir. Thanks.
So we have one question over here. In differential amplifier with active load part 2 with non-zero lambda n and lambda p, sir took voltage source of M1 0 despite finite resistance. Voltage at source of M1 0 despite finite but reasoning behind it I couldn't understand. That the swing at drain M1 is low, equal to minus GMN PGMN. Um, So you are talking about you are talking about single to differential to single ended uh, circuit only, right? Okay, so let's draw that. So this is the differential to single ended circuit, right? So what you are trying to ask, the lambda n and lambda p sir took voltage at source. So can you help me in labeling the transistor? Is this one correct? You can turn on your mic and then speak also, if that will. The lower left is M1, okay.
Sir, it will remain saturation only.
M1, lower left is M1, then this is M2 or this is M2? The PMOS is M2 or the NMOS is M2? Okay, this is M2, then this is M3, M4. Is the labeling correct? Okay. So, what is a doubt? That sir took the voltage as source of M10 despite finite resistance, but reasoning behind it, I couldn't understand. So, basically, the source of the M1, how it happens is, let's say you had two circuits over here. That swing at drain of M1 is low and equal to minus GMN over GMP times VD, and the drain of M2 is not swinging tied to zero. Drain of M2 is not swinging. Is it grounded over here like this? So you want to find out, uh, are you talking in this fashion? Sir also drew zero voltage where he was finding the short circuit current. Okay, okay. So the circuit, I believe, was something like this, correct? Okay. So what basically, like, if you actually see, as far as a real circuit is, so you understand that had these two circuits been perfectly symmetric, then this voltage swing would have been zero, absolutely zero. You understand this, right? Okay. Now, I understand that these two circuits are not perfectly symmetric. In this case, where there is actual this thing, there is actual ground. However, here there is not an actual ground. So, but still, the looking in impedance over here will be 1 by GM4, right?
in parallel with ROP, sir.
In parallel with ROP, but yeah, in uh, yeah, RS P parallel ROP, correct. So what is basically GM4? GM4 is a very GMs of the transistor are very huge in comparison to. So basically, let's say if you need to see let's say there is a swing over here, let's say looking in impedance from here, you see. Okay. So in that case you will have this huge block of output resistance, and just a minute, uh, 1 second. mm,
Based
so
on gain also we can approximate it, right? So GMRO to ROP should be much greater than 1. So if like that
yeah,
way,
yeah, wait, let's try to see, so basically we want to see that whether the looking in circuit from here and looking at circuit from here, these two should be roughly equal. This you want to basically make sure, am I right?
it should not be equal, right? It is not
No,
symmetrical.
it won't be equal. It won't be equal in practice. But yeah, as far as a zeroth order analysis is concerned, we have to prove that these two circuits are roughly equal. So how will you proceed to do that? So let's call this Z1, and let's call this Z2, where Z1 and Z2 are looking in impedances of the two cases. Okay. So now in this case, so can you tell me what is Z2 quickly?
Looking from source, sir. Source, no, sir.
Source of M2, correct. Yeah, so it's basically 1 by GM2 parallel RO. Okay, RO2. And here basically these two transistors are ideal. So we let's call GM1 equal to GM2 equal to GMN, and RO1 equal to RO2 equal to RON. And for the upper transistors, GM4 equal to GM3 equal to GMP, and RO4 equal to RO3 equal to ROP. You have this, okay. So Z2 you have got, it's basically 1 by GM2 parallel RO2. Okay, now let's try to compute Z1. So for computing Z1, you basically have GMN over here. This is grounded. RON over here, and then here basically you have diode connected transistor M4. So here basically what you have is GMP parallel 1 by ROP, okay, which can roughly be written as, sorry, 1 by GMP parallel ROP, which can roughly be written as 1 by GMP. Do you agree?
Yes, sir.
Yeah. So now let's try to find out, let's put a voltage source over here. Let's call this VT. So what you have is the current that is flowing in this direction is GMVT, and current that will be flowing, let's call this voltage as some Vx. Okay. So current that will be flowing in this direction will be RO, like GMN, sorry, Vt minus Vx times RON,
RO. Mm.
RON, sorry, divided by RON. So the total current that will be flowing inside this 1 by GMP, 1 by GMP will be GMVT plus Vt minus Vx times 1 by RON. So this current and this current will combine, and total current will flow inside this.
Yes,
And
sir. VT. It should be VT, right?
no, it won't be Vt. It will be basically equal to GMP times Vt.
Mm, yes, sir. Yeah.
This you understand, right?
Ah, yes, sir. Yes.
GMP times, sorry, what this this times GMP will be Vx. Yeah, this time GMP will be Vx. This is correct. You understand this? Sorry, this. Sorry. 1 by GMP. Okay. So from here, what you can get is GMN times Vt. So we can put this as Vt times GMN plus 1 by RON minus, that is a here we will have GMP, and over here we will have Vx times, we can take GMP over here. So we'll get rid of GMP over here. So it's GMN RON, and here inside this it is GMP plus 1 by RON. Now in this case, you can see that like in GMN plus 1 by RON, and in GMP plus 1 by RON, this 1 by RON can be removed, right? You understand this? Yeah. So this is basically GMN is roughly equal to Vx times GMP. That means to say Vt will be, mm, I have not made a mistake here, right? GMN divided by GMP. This is basically Vx. So if this is Vx, that means to say, so if this quantity is Vx for you, that means what is the total current? What was basically the total current? Gm times Vt plus Vt minus Vx by Ron, correct? So It is equal to Gmn times Vt plus Vt minus Vx divided by Ron. So we substitute the value of Vx from there. So Gmn times Vt plus Vt by Ron into 1 minus Gmn divided by Gmp. So this is basically equal to Gmn plus 1 by Ron divided by 1 minus Gmn divided by Gmp, correct? So if you rearrange it, what you get is Gmn times 1 minus 1 by Ron times Gmp plus 1 by Ron. This is correct. This times Vt is equal to It. This is correct, right? Is there any problem in this? No, right? Okay. So basically what you have is Vt by It is equal to 1 over Gmn times 1 minus Ron Gmp plus 1 by Ron. That means to say, and this term will be much higher than 1. It is basically output resistance of a transistor multiplied by transconductor of a transistor. So this term will be much higher than 1. Uh, you agree with that?
Yes, sir.
Okay. So if this term is much higher than 1, then this basically can be written as roughly Gmn plus 1 by Ron, correct? So this is basically almost equal to Z2. So due to this term being very small, so even though there is some mismatch between current of like in looking in impedance from one side and other side, but this difference being very small, you are still that node is still at 0, and so you can see over here if Ron was infinite. Yeah, correct. So if Ron was infinite, in that case, this term would be absolute zero, which basically means to say that there is no Ron, then there is no difference between looking in impedance from both the cases. But if Ron is finite, and as the Ron keeps on reducing and reducing, the efficacy of that node starts swinging slightly, and once that Ron is very huge, then that approximation that the drain of transistor M1 will not swing, will just go away. And in that case, basically, you can't say that the source of M1 and M2 are at virtual ground, are at differential ground. It is clear, right? Any other doubts? Okay. So, based on this differential amplifier stuff only, we will try to solve one more question. So, uh, let's see
Sir,
this question. Yeah.
sir, for cadence, do you follow any tutorials, sir? Means I am at initial stage. Means if I want to get expertise with the tool to fully, where can
Uh,
I find the resources, sir?
See, like as far as getting familiarized with cadence, you have videos on YouTube. You can look over on that and
Hafiz, no, sir.
yeah, that Hafiz KT, something like that.
Yes, sir, but he didn't explain. I mean, for basic level, sir, what and all you saying, no temperature and all. For a high, means that one I am able to do, sir. Basic things and all. If
You
I
can
want to do,
so there is a help section in cadence also, if you see.
mm, mm,
So you can look over like various see basically DC analysis if you do
mm,
there let's say you go to the help and type DC analysis. In that
mm.
case, you will get what all options you have in DC analysis, how you can use it. Those things you can see over there.
Even for S parameters, that one also RF and all also.
Yeah, like every in help you will find documentation for all the analysis that is possible and all the various components of the analog lib library that you have. All those things you can find in that particular section.
Sir, after typing help, there would be the
No,
one will be written.
see, I will. I don't have the cadence window right now, but the complete basically window that you have, no, yeah, whether you have ADL, ADXL, like
Yes,
on
sir.
the menu bar, there are several, there is option, simulation. There you will find the help also. In that, you can type and explore that particular thing.
Okay, okay, sir. Yes, sir. If I have any doubt, can I ask next week, sir?
Yeah, yeah, sure. Any other issue?
Fine, sir. Yes.
Okay, so we will go to we will solve one question. So we have seen that in fully differential circuit we have VCM plus VD and VCM minus VD, and let's say this is VDD. Okay, so in this case, let's say your VDD is very high. So how will you find the swing limits of the circuit? You guys have what all what will be the two conditions for its swing limit? Let's say
Yes,
this
sir.
is
Get.
GM,
Mm.
this is GM, and some VCM is given. Let's say VCM is fixed to some voltage. So how will you find the swing limits?
Sir, based on that condition, VDS should be greater than VGS minus VT. So
Uh,
yeah,
so basically, you have two conditions, right? One that transistor can go into triode, other that transistor can go into cutoff. So let's say for ease of the analysis, I just take the differential half circuit of this problem. So differential half circuit will be nothing but a common source amplifier, right?
yes, sir.
And you have VD over here. So what is VD plus some VCM? And let's say this voltage is some VD, V capital D or VCM out. So what if there is incremental voltage of VD over here? What will be the incremental voltage at the output? And this is GM.
Yes, sir. Sir, minus GM into R into VD, sir.
Minus GM into R into VD. Okay.
Hmm.
Now first condition we will take for it going to be in triode. Okay. So for this transistor to not go into triode, what you will have to do?
Sir, then VCM, yeah, VCM minus GM R naught should be greater than VCM plus VD, sir.
VCM plus VD should
Hmm.
be greater than,
Hmm.
should be less than or equal to, uh,
So we not going to triode region, right?
yeah. So basically drain should be at least, drain can go at max 1 VT below your gate voltage. So that means VCM plus VD should be less than or equal to VCM out minus GMR times VD. Okay. That means to say VCM minus VCM O, or basically 1 plus GMR times VD should be less than VCMO minus VCM, this minus VT, sorry, plus VT. Plus VT. That means to say VD shall be less than or equal to VCMO minus VCM plus VT divided by 1 plus GMR. Correct? This is basically condition for triode. Okay. And what is the condition for cutoff?
Sir, get to source voltage should be greater than VTH with VTH.
Correct. So we will, so basically whatever current, let's say this current was I, so that means to say I by 2 will flow in this and I by 2 will flow in this. So basically GM times VD must be greater than or equal to, must be less than or equal to I by 2. So that goes to say VD shall be less than or equal to I divided by 2 GM. Correct?
Yes, sir.
Okay. So
Maximum voltage also we will calculate based on this, right?
correct. This basically you have. Now generally, so these are basically the limits that you, these are the hard limits. After this, your op amp, your differential amplifier will become useless. Okay. But there is even if the hard limits are not hit, but in and you are still in the range of active operation. So let's say you had R over here and some VCM plus VD over here, correct? So even if hard limit is not hit, but still the gate voltage of this transistor is changing, correct? So if the gate voltage of this transistor is changing, just a minute. If the gate voltage of this transistor is changing, that means to say that the and what is basically GM? GM is equal to mu n Cox W by L VCM plus VD minus VT. Correct? You follow this?
Yes, sir.
Okay. So if this is the gate voltage, if this is GM, so you notice that even though the transistor won't actually go into saturation, will actually not go out of saturation within these limits, but your GM is still dependent on the input voltage. That means to say, what will happen is if GM is dependent on the input voltage, what will happen in that case? So whatever VD changes, due to that GM will also change. And if the circuit parameter is also changing due to the input, that means to say that input won't be the output won't just depend on GM times R. So what is output basically? Output is GM times R. And what is GM times R times VD? Minus of GM times R times VD. And what is this equal to? Minus of GM. What is GM?
mu and Cox VCM plus VD.
Mu n Cox W by L times VCM plus VD
VD.
minus VT times
Hmm.
VD.
Yes, sir.
So basically, there is a VD square also involved here, right?
Yes, sir.
So that means to say that your system is not linear anymore. You understand?
Yes, sir.
What is a linear system?
Yeah, I mean, V out by it should be it should follow the super homogeneity and that position, sir. Here VD.
Superposition and homogeneity, that is correct, but yeah, so
Hmm.
here basically so linear system means that your output is dependent on the input, but here your output is also dependent on VD square along with the input, correct, along
Yes,
with
sir.
the original VD. So that means to say that but in actual you want linear system. So there is one increment to the system. So basically, what you see, why the system is non-linear? Because your GM is depending on the input voltage, correct?
Yes, sir. Means we need a non-linearity because of we will get power amplification. If it is a linear, we don't get power amplification, sir. That one also.
No, no. It should be non-linear. It like in actual that is non-linear. But as far as small signal is concerned, you this system should be linear, right?
Oh, yes, yes, sir.
Yeah. So basically, what you want is that this system, your GM, should be independent of your input voltage. Okay. So let's try to look at another circuit. Let's say this is R2, this is R1, and you have input over here. In this case, here there is VCM plus VD. What will be the voltage over here roughly?
Sir, it should be one plus GMR GMR R2 by one plus
There will be
GMR.
some VCMS, let's call it, some
Hmm.
voltage, some voltage source plus VD divided by 1 plus GMR2. I hope by
Yes, sir.
this point of time you can write it without calculating.
Yes, sir. Yes, sir.
Yeah. So you have this over here. Now, what is the GM of this transistor?
Mu and okay, okay. VCM minus VD uh, minus VCM
VCM plus, so it will be basically mu n
COX
Cox
double
W by L times VCM plus VD minus
minus VCM minus
VCMS
hmm,
minus VD divided by 1 plus, sorry, GMR2 into 1 plus GMR.
hmm.
minus
Sir,
Vt.
yes, sir. Sir, in single equation we can write VD get cancelled. So VD by 1 plus GMR R2.
Correct.
Mm.
Just a minute. 1 second, guys. Yeah. So it's basically VCM plus VD minus minus VCMS minus VD times GMR2 upon 1 plus GMR2 minus VT. Correct? So you have this over here. Now this GMR2 upon 1 plus GMR2, what you will get? This is roughly 1, right?
Yes, sir.
Okay. So this is if this is roughly equal to VD, that means to say that mu n C this GM is basically mu n C of W by L times VCM plus VD minus VCMS minus VD minus VT. Correct? So VD and VD can be cancelled. So this is basically equal to mu n C of W by L times VCM minus VCMS minus VT. So now you see that your GM that was only non-linear component of the circuit is now not dependent on the input. Correct?
Yes, sir.
So now your circuit will be much more linear.
Sir. Means through source degeneration we can achieve linearity. At the same time, we can reduce the slope of the drain current equation, no, sir, in channel length modulation.
We let's not go into, yeah, that we can do, but let's not go into channel length modulation. Here basically that is a different thing. So here basically we see that using source degeneration we can actually improve the linearity of the circuit. Yeah, so now it is independent of the input voltage. So let's say I wanted to implement it in differential pair. So how will I implement it? We will have R over here. We will have VCM plus VD over here. We will have R2 over here. And this is grounded, right?
Yes, sir.
So we will have this kind of circuit over here. VCM minus VD. Correct?
Exact. Yes, sir.
Yeah. Now, if this is the case, so what we will, now you can see that, so compared to this circuit, if we compare this particular circuit, the original circuit that we had, plus VD and here VCM minus VD. So in this case, in the new circuit, we basically there is additional voltage drop across R2, right? Yeah. So if there is additional voltage drop across R2, that means to say that so the amount of VDS that this transistor would have got in this circuit would be much larger than the amount of VDS that the transistor gets in this particular circuit. So that means to say that the voltage headroom that this transistor and this current source has in this circuit has now reduced. So can you think of a workaround to have this resistance R2 and at the same time not have the reduction in the voltage headroom.
Sir, by while placing the R2, we get a linearity, and it is acting like source regeneration, sir.
Yeah, we want, so basically we want source degeneration in differential circuit only, right?
Mm.
In common mode, it is not required.
Mm. Yes, sir. Yes, sir. Exactly.
Does everyone understand this? So if it is not required in common mode, what you want in differential mode, your circuit should look like this. Just a minute. Your circuit should look like this, correct? So you want a ground over here in differential circuit. Now to achieve this ground, what so basically you have seen that if this is half circuit A and this is half circuit B, if you connect identical, so this has VCM plus VD and this has VCM minus VD. So if you connect identical nodes of these two circuits, you will get a differential midpoint will become ground incrementally, correct? So basically what we will try to do is we will try to achieve this ground that is present in the circuit by doing actually this. So what can be done is as follows. We have resistance over here. We have VCM plus VD over here. And we want that in common mode, we should only see three stacks, this resistor, this transistor, and this current source. So we put a current source over here. So in common mode, we have these three stacks and we put R2 like this. Okay. And we have another circuit over here and we have R2 like this. So if I connect these two points, that means to say that this will become a differential ground, right?
Yes, sir.
Okay. So if we have this circuit in place, VCM plus VD, then you have 2R2, VCM minus VD. So this now doesn't eats up in headroom, and in differential this has this degenerate resistor of R2. So this will basically be a much more linear circuit as compared to the original one. You understand this? So instead of this now, like earlier the tail current was seeing zero voltage swing. Linearity comes at cost of finite CMRR. Yeah, correct. Here, no. Let's consider this. Let's consider the CMRR is also infinite. Uh, let's see what is the common mode half circuit of this. The common mode half circuit, this 2R2 will just go away, right? Yeah. So if 2R2 goes away, so that means to say you have basically this VCM and you still have CMRR as infinite. In incremental things, CMRR will definitely be infinite. But one thing is that now, like if this VCM swings a little too high, then basically this particular current source has possibility of going into triode. Okay. which was not the case in this particular stuff. Okay, so incrementally CMRR has not changed, but for a large signal, there, it might so happen that this VCM swings a little too high, and this transistor might go in triode. So, for a large signal case, there is definitely the issue. But the VCM doesn't swings that much, so you can still be done with whatever you have right now. The only drawback is that drawback you will understand if you have you have learnt about noise. Do you know how a noise is generated in a system in a current source? Okay, so that you will learn as you go. Like a brief overview I will try to give. So let's try to compare these two circuits. And we have this over here. So let's say there is some disturbance in the current source. Okay. And the output you are taking differentially. So if there is some disturbance in current source, that disturbance will equally go on the both of the nodes, right? So if that disturbance equally go on both of the nodes, that means to say the difference in the voltage that you take as the output, that won't be affected by any difference that is caused in this current source. Do you follow? Okay, but if there is some difference in current source over here, then in that case, and let's say this difference, this disturbance is different from this particular disturbance. Okay, so in that case, the distribution will be unequal, and so it will basically whatever differential voltage that you take between these two nodes will result in non-different non. So any different any disturbance in current sources now will result in non-zero differential voltage. So basically, your circuit has become more prone to disturbances, disturbances, like formal word for this disturbances is called noise. Your circuit has become more prone to noise, but at the cost of better linearity. So there is always a trade-off. You understand this?
Yes, sir.
Yeah. So, is there any other doubt, for the content that we have discussed so far?
No, sir. Sir, but sir, from I need uh, one question for a GM or not of it gain the way how you will proceed.
Sorry, GMO, which one?
GM into or not means in week 6 problems. Sir.
Uh, which question you are talking about? Is there any doubt in some question? Is it?
Yes, sir. Yes, sir.
Just a minute. I will try to share my screen. For, is my laptop screen visible now?
Yes, sir.
So you are saying week 6.
Yes, sir.
Which
Sir.
problem?
Sir, for every problem, they asked gain as a GM into or not into 10, right?
GM into R naught is equal to 100.
Yes, sir. Gain. It is nothing but gain, right?
Yeah.
So the means if you tell me the way to proceed now, sir, it would be helpful, sir. That's right.
No, there. See.
And the largest sinusoidal input to proceed. Just a hint, sir, not an exact answer. Hints.
Um, uh, it's a straightforward problem. No, that's what I mentioned. The same thing you can use. So basically, like in all these transistor, you just put some. So let's say you assume this transistor to have transconductance of value Gm. You put a resistance in parallel to this with a value of 100 by Gm. Okay, that will just add one more element to your circuit, to your small signal model. In parallel to GM, you just add a resistor of 100 by GM, and then proceed with like the circuit solving technique that you know.
Okay, means I thought gem or not to get that gain means by calculating channel length modulation or not, or lambda is zero. How we can proceed? I'm
No,
like
no, lambda is zero. That has to be assumed for the first part only. But like for the latter parts, instead of actually giving you the lambda and like asking you to calculate the output resistance, it's just said that lambda is such that GM into RO comes out to be 100. So, if you would have been given actual value of lambda, you would have calculated the actual value of output resistance R out, and from there, and that you would have placed in parallel of these transistors. But now, since you have been given GM RO into 100, GM RO is equal to 100. In that case, you will just assume a resistor of value 100 by GM and place it in parallel to these transistors and then proceed with circuit analysis.
yes, sir. What I thought, no, sir. If lambda equal to zero is channel length modulation is not considered. Then how that a GM or not will be 100? I thought I mean that illusion. I didn't get any thought to proceed. Here you simply said at the thought at the time I get this thought. No, I can solve simply.
Okay, no issues, no issues. It's just lambda equal to zero is given only for the first part of the problem. For latter parts, yeah, the lambda value is non-zero.
Okay, okay, sir. Yeah, I get the point.
Yeah.
Thank you, sir. Thank you, sir.
Any other doubt?
Fine, sir. Everything is fine, sir. As of now.
Okay. So if there is no doubt, this was it for the session. Thank you for attending.
Thank you, sir. Thank you so much, sir.